3D design of the vanes and the runner. We do it using the inverse design software Turbine 1, and once you launch it, this is what you see. This is the GUI, and the way we start is we open the file which was exported from TD-Pre. So we can see there are 3 files exported from the mainline code. So one for the stay vane design, one for guide vane, and one for the runner. So let's start with the stay vane first. And once we open this, we can see all of our different sections have been filled by information from that TD-Pre file. And in Turbo Design 1, we follow a top-down approach in this tree. And so starting with the specifications tab first, what we can see here is these fields, all these have been pre-filled using the TD-Pre file we imported. So we can see the fluid properties for water here, the volume flow rate, and the number of plates as well. So these correspond to the stay vane. Now let's look at the next section, which is meridional design, and we can actually enable the plot here and see the flow comes from top to down like that. And we can also see this 2-dimensional grid here. And one thing to note here is, although the grid is 2-dimensional, but the solver is still 3D, and it's because it solves the third dimension is solved using a Fourier transform. And so even though it's a 3D solution, but it's still very fast. Next comes thickness, and the thickness of the blade can be specified in a number of different ways. So we have the option of normal or tangential thickness, and then if we select normal this time, then for the streamwise distribution from leading edge to trailing edge, we also have different options like constant or control points, or this time we go with NACA profile, where you just need to specify the NACA code. And again, this comes from the TD-Pre file as well. The next section is blockage, and this is something we use only for very high speed transonic cases with significant boundary layer blockage, and so we don't need to use it for this case. The next section, which is very important in inverse design, is blade loading. And we first open the plots, rearrange them a little bit. Now what we see here on the left is the span-wise work distribution, and this red is leading edge, green is the trailing edge, and 0 means hub and 1 means the shroud. And here we can see it's a free vortex distribution, so there is a constant value of the work coefficient from hub to shroud. And we can see how the stay vane increases the swirl from leading edge to trailing edge. And so once this work is fixed, the next step is also to specify the streamwise distribution of blade loading at the different spans. And here we can see the same distribution has been specified for both hub and shroud, so which is basically a 4-loaded kind of distribution here. So once this blade loading has been specified, the next option to specify is stacking, but in this case we go with a radial stacking because we don't really specify this for the vanes, we only do it for the runner. And once this is set up, we can run the solver to generate the stay vane. And we can see very quickly, in 5 seconds or so, we have our stay vane design. We can have a look at how it appears in 3D view. And so once the stay vane has been designed, what we can do is in the project manager window, we can see some results which come from the inverse design code, which is the inviscid solution. So we have some performance parameters here, such as an indication of the profile loss, which is very important in stay vanes, and also some other parameters of interest. And then there are some geometric parameters as well, for example, throat. And profile loss is important, so we can select this and also the throat, and then we can choose to see only the selected variables of interest. And then what we can do is we can rename this to stay vane. And once the stay vane design has been achieved, the next step is to design the guide vane. And so we can choose import from here, and we choose the TD file which was exported for the guide vane. And once this has been imported, we can see all of the different sections have been updated for guide vane. And so the specifications have been updated, and then the meridional design, this is actually for the guide vane. The thickness, it's a Naka distribution as well. For the blade loading, what we can see this time is the default loading has been specified as a mid-loaded blade. And for the span-wise work distribution, we can see the RVT star has further increased from leading edge to trailing edge. And one thing to note here is the leading edge value for the guide vane is the same as the trailing edge value from the stay vane, and this is to ensure a good matching between the two components, and so that the incidence coming onto the guide vane is correct. And once all the sections have been updated, the next step is we can run the design to generate the guide vane. And again, very quickly, in less than 5 seconds, we have the design for the guide vane. And we can also see new properties have appeared in the project manager window, and these values actually for the profile loss and throat, these actually correspond to the guide vane. So change this to, rename this to guide vane. And then finally, the last component to design is the runner. And so in this case, we will go back to import, and this time select the file for runner. And the sections have been updated as before. You can see the specifications have been updated. The number of blades has changed from 19 to 13. 13 is the number of blades in the runner. And now we also see a rotational speed, a non-zero rotational speed has appeared here, 1500 RPM, which we specified in TD pre. Now meridional design, we can see the 2D grid for the runner, and we can also see layering has been used to concentrate the grid points near the leading and trailing edge. And this is because runner design is a bit more complex compared to stay vanes and guide vanes, so we need more concentration near the blade edges. For the blade thickness, we again specify a Naka profile, and this is the default thickness. And as we can see, the hub distribution, the hub thickness is a little higher than the shroud. And this comes from TD pre as well. And we still don't need any blockage for this low speed incompressible flow. And now the blade loading for the runner, it's if we have a look at the span-wise distribution first, then what we see is the leading and trailing edge values have reversed. So the leading edge value is actually higher compared to the trailing edge. And this is because we have swirl at the leading edge coming from the guide vane, but then we don't need any swirl coming out of the runner. So we want an axial flow at the runner outlet, and that's the reason we have a zero swirl from hub to shroud at the trailing edge. And the leading edge, this value again is the same as the trailing edge of the guide vane that we saw earlier. Then again, this will ensure that the incidence coming onto the runner leading edge is correct. And finally, the blade loading, the stream-wise blade loading for the runner. This is the default loading that came from TD Pre, and we can see a fore-loaded hub and an aft-loaded shroud in this case. And for the first design, we can go with the default stream-wise loading. Stacking. Now this stacking is actually the wrap angle, and this can be specified at any of the streamwise location as we need. And usually in Francis Turbine runners, we specify it at the leading edge. So 0 location means the leading edge. And this is where we can actually specify the wrap angle variation from hub to shroud. So using different options available to us, and in this case we can start with a 0 wrap angle, 0 stacking, which means a straight or a radial leading edge. And once all these inputs have been specified, we can run the solver again, and once again we have our design of the runner, and this is how the runner blade looks. And we also see we have some new results in the project manager window, and we can clearly see profile loss is pretty high compared to the other components, and the throat value is visible as well for the runner. So let's first rename this to runner. And once we have this in TD1, there are also some post-processing options we can use. For example, we can create a 3D plot of the different components. So what we see here is only the runner. And if we also want to see the stay and the guide vanes, we can select them from the project manager window. And then in the 3D plot window, we can enable all the blades to be visible, just like this. And also what we can do is, if we want to see the relative arrangement, the relative locations of the different components, we can simply select combined plots, and now clearly we can see all the 3 components in their correct locations. So the stay vane followed by the guide vane, and then the runner here. And then we also have an option to create a 2D plot. So a 2D plot of any variable of interest. For example, if we choose to go with the static pressure in this case, and we can maybe select 3 different span locations. So 0 is hub, 0.5 is the mid span, and 1 is shroud location. And so we can see the dotted lines here. This starts with the stay vane at the top, which is very mildly loaded, followed by the guide vane here. So it's a little highly loaded than compared to the stay vane. And finally the runner, clearly it's very highly loaded compared to the other components. And we can also notice the pressure drop from leading edge to trailing edge. And also the distribution is quite 3-dimensional. So unlike the distribution for the vanes, which was pretty much prismatic 2D, but for the runner we can see there is quite a variation from hub to shroud. And after this, we can also choose to see some 2D plots in the project manager window like this. And what we can do here is we can select a parameter of interest, and this will be plotted in front of us in this 2D plot here. And so the first one corresponds to the stay vane, then the guide vane, and then the runner. And what we clearly see is that the profile loss is the highest inside the runner. So the runner is the source of the highest loss in the entire among these three components. And so if we desire to increase the efficiency of our Francis turbine, it makes most sense to optimize the runner. And this is what we are going to do in the next step when we do automatic optimization. And once we have designed all of our components here, what we can also do is we can use these export options to export the different components for various studies like CFD or FEA. Now, in this case, for example, if we want to do a CFD study, then we need to first specify whether there is any specific type of leading or trailing edge we need. So we have the option of elliptical, tangential cutoff, and normal cutoff, etc., both for the leading edge and the trailing edge. Then we can specify the domain. So for example, if we are looking for CFD or FEA, and in this case we can select a CFD single passage. And finally, for the output, we can specify the different formats in which we need that single passage. And for example, for TurboGrid, it's going to give us the curve files. And finally, we browse to the correct location to export our curve files for the CFD analysis.